Good afternoon, everybody. Welcome to GTC. Hopefully you are enjoying it. And first of all, I want to say, what a year, especially for us AV developers. In 2025, I would say that it's also the ChatGPT moment for autonomous driving technologies, mostly because of the rapid progress of AI technologies. We have VLA, vision language action models, and we have word model foundation models, and we also have reasoning models. With these technologies, I would say over the last few years, we have been seeing the way we develop AV have been fundamentally changed. Sorry. Good timing. On the other hand, these changes didn't really slow us down, though. And on the contrary, we are seeing the whole industry is moving much faster towards full autonomy. And at this moment, I would say that the path to full L4 level autonomy has never been this clear. And also the mission to make everything moves autonomous have never been this real. And NVIDIA actually have been working on this problem, I would say the autonomy challenge for a long time, for more than a decade, actually. I remember 10 years ago, we produced our first, I would say, ADAS device or ADAS chip, which is called, which is called the Parker. And that device actually enabled the first generation of autopilot. And 10 years from that, today, when we're looking at a pivotal moment of AV industry, obviously NVIDIA is working super hard. My team is working super hard with the rest of the industry and the ecosystem to find a path towards scalable and a safe level for autonomy. And in this presentation, I will just walk you through what we have been doing, all right? To kick off the presentation, actually, I would like to first show a video, which is what my team did recently, drive from San Francisco around the North Bay, based on a reasoning model in a prototyping vehicle from our partner, Mercedes. All right, let's get the video rolling.
Today, we're going to experience the reasoning capabilities of the Alfa Romeo model that powers the intelligence in our cars. Throughout the drive, you'll see the car is constantly evaluating its surroundings in real time. You can also ask the car for information about your surroundings. Hey, Mercedes, why is the Transamerica pyramid shaped like that?
Architect William Pereira chose the tapered design so more sunlight could reach the streets below instead of casting a huge shadow.
We've also asked the car to narrate its thinking out loud today, so you'll hear it call out what it's observing and why.
I'm changing lanes to the right to follow my route.
Alfa Romeo is continuously reasoning in the background so that when something unexpected happens, the car is already ready to act.
I want to turn left, but there is oncoming traffic, so I'm waiting for a gap. There's a double parked vehicle in my lane. I'm going around it. There's a pedestrian in the crosswalk ahead. I'm going to yield. There's a vehicle crossing my path ahead. I'm going to yield.
What sets Alpamayo apart is how it reasons through complexity, breaking down edge cases before they become problems. Hey, Mercedes, can we speed up?
Sure, I'll speed up.
Hey, Mercedes, make a lane change to the right.
Sure, initiating lane change.
You know, I think maybe we should go to Sausalito to grab a coffee. Hey, Mercedes, can you take the next exit, please?
Sure, turning right ahead.
Hey, Mercedes, pull over here.
Sure, I'll find a safe place to drop you off.
From dense city streets to highways and bridges, in both real and simulated environments, Alpamayo reasons through it all, continuously building a safer, smarter driving experience.
There's a pedestrian in the crosswalk ahead. I'm going to yield.
Hey, Mercedes, can you pull over here?
Sure, I'll find a safe place to drop you off.
Alrighty, hopefully this video, thank you. I think my team does deserve a round of applause because they have been working super hard. And hopefully, toward the end of this year, we can really have the customers and let's say other folks to be able to experience this in a real car. Hopefully, this video again gives us a glimpse of the future, how a reasoning model can be used to tackle the autonomy task. And these slides, obviously, I believe Jensen has been using the slides in a few of his keynotes, and this shows the journey we have been through in the AI technology development. With AlexNet in 2012, I think, and then Transformer in 2017. We have been seeing perception AI evolving to generative AI. And with reasoning model, which is happening right now, we are introducing agentic AI. And my team and obviously the rest of the industry are working on also putting this AI technology into a physical embodiment, which is the physical AI. And we believe that building and safely deploy physical AI is going to be the defining challenge of the coming decade. And since automotive, they are just basically driving robots on the road, I'm pretty sure AV will be the first mass-produced and mass-deployed physical AI technology and applications. And why is autonomous driving so important? I think there's a few numbers here. So the most important number here is actually the middle one. Every year, across all different segments, roughly speaking, there's 13 trillion miles being driven by a car or a delivery motorcycle, a delivery car, and obviously there's other use cases as well. And as of today, only 0.006% of the mileage are driven autonomously. And we do believe that in the near future, every mile, everything that moves will become autonomous. And this gap is the huge opportunity in front of all of us, even for the size of NVIDIA. And to tackle this challenge, as I said in the beginning, at this pivotal moment, we are also pivoting our main basically product, which is NVIDIA DRIVE, to a slightly different form. So, as Jensen mentioned, physical AI problem is a three-computer problem. So in DRIVE AV, in NVIDIA DRIVE, we have really three computers, the training computer and the simulation computer in the cloud, and the inference computer in the car. And we are going to build 5 layers of services on these 3 computers. And on the bottom layer, obviously, it's our hardware. And here it's the DRIVE Hyperion. And it provides a unified reference design for compute and sensors. And on top of that, it's the operating system and the platform software. This is what we call the halos. Halos provide the middleware that interacts the model and our hardware. And also, in the future, we want halos to be able to provide safety guardrail for anybody who wants to deploy an end-to-end model on our Hyperion hardware. And on top of that, we have the model layer, where we use, I guess you guys have heard about Automotive, and we have open sourced, a version of Automotive, and we will keep developing on that. And on top of that, it's applications. This is where DRIVE AV come into play. And we are working our partners to deliver from partial to full autonomy in our basically in-house full stack. And last but not least, infrastructure is very important in the age of AI. We are building a bunch of foundation models and tools in the cloud to help developers to develop efficient models to be able to run our hardware and the full stack. Let's get into a little bit into the details. And as I said, Hyperion is a unified vehicle reference architecture towards L4. And at the core of it, obviously, it's a L4-ready, compute architecture, which is based on a dual, basically, AGX SOAR, which is our flagship device of current generation for in-car SoC. And on top of that, we are also providing a reference design for the sensor suite in Hyperion as well. And this is very important because only when you have a unified sensor architecture, the data will become shareable across different OEMs, different platforms. And on top of that, we are also working with our partner, Uber, to build a fleet of basically Hyperion, the current generation called Hyperion 10, Hyperion 10 sensor set, and to do data collection and give a sort of jump start to the whole industry. I think this is very important of our strategy as well. A little bit more regarding our current flagship device, AGX SOAR. This is really an in-vehicle AR supercomputer. It's based on the Blackwell architecture, which is the same architecture as most of the company are using to train the foundational models. And it supports basically, obviously different precisions, starting from 32 to 16. It also supports, floating point 4-bit floating point, which is very important because for in-car devices, you are always limited by memory bandwidth, and this can effectively increase your in-car compute capability. And as compared to the previous generation, if we can, use FP4, that's really basically a 20x boost in terms of performance as compared to Orion. And the sensor suite. Again, to make a sensor suite, common is very important, as I said, from a data shareable perspective. And we have 2 models. On the right side is the high model, which we believe will be able to sufficient for high-level autonomy, including highway and urban L3 and L4. And right now, this sensor suite has 14 high-definition cameras and up to 4 internal cameras, and it has 9 radar and 1 LiDAR. The sensor is designed to have full sensor redundancy, so that whenever you have single point of failure, the system will still be able to operate safely. On the left side is our base model, and this is obviously more focused on the cost, saving in terms of at the BOM level, but with 10 cameras and 3 radars. This system will be able to deliver a full hand-free highway and urban address-to-address, even park-to-park capability, which is what we are building on with our customers in Drive AV. And on top of Hyperion, we build Halos. Halos, as I said, is a unified software safety foundation for L4. It actually has multiple layers of software defined within Halos. At the bottom layer, it's our operating system, which is certified to the highest ASIL level, which is ASIL Delta. This is based on the legacy Drive OS, basically software, and Drive OS will become part of Halos moving forward. It provided a library, including CUDA TensorRT and LLM SDK, so that we can enable developer to deploy large language model and Gen AI models for AV in the most effective way. And it also supports both Linux and the QNX, basically, operating system. And on top of that, it's a middleware. So middleware is very important. In our current generation, which is Orion-based generation, we used to have a separate responsibility between NVIDIA and OEM. And OEM actually have to spend hundreds of engineers to define this sensor and a vehicle, let's say, abstract layer. And moving forward, in Halos, as part of Halos operating system, Halos OS layer, we will take more responsibility. And because much of this software is generalizable across different OEMs, we can significantly reduce the burden, engineering burden on the OEM side to be able to deploy their stack on Hyperion. And on top of that, in the future, in the SOAR generation, we also want to introduce as I said, the safety guardrails for the system. This will including our 5-star ENCAP and NCAP active safety software, and it will have our classical stack so that to serve as a guardrail. So in the future, hopefully for every AV developer, they can put their own end-to-end model on Halos, and benefit from the safety foundation we have built across different layers within Halos. Now let's go to the model layer. And today, I'm very proud to announce that we are going to release Automotive 1.5. And Automotive 1.0 was released only, I think, 2 months, slightly more than 2 months ago. And it was a 10 billion parameter model, which is also the first reasoning model for AV. Over the last 2 months, it was actually number 2 in the most downloaded application or model in the whole robotic space on Hugging Face. It was downloaded more than 160,000 times. I didn't even know there's so many people working on AV. But we are very happy about what the result. And in Automotive 1.5, it's still a 10 billion parameter model, but we are going to make it more powerful. So what are the changes? Number one, we are going to introduce routing capability into the model in different formats. It can be waypoints, or it can be nav guidance from a, let's say, a navigation software, or in some, let's say, vectorized format. Then the model will be able to follow the route. And number two, we are also introducing text prompts capabilities. As what you have seen in the video, in the opening video, the driver or the passenger can ask what the car is trying to do. We are also introducing multiple configurations in the camera support. It can support 1 or 2 or 4 cameras with different FOVs and placements, so on and so forth. We believe that with this model, it can hopefully add one more capability, one more capable model to our ecosystem and help the industry build more advanced models. And as a matter of fact, our Automotive 1.5, ranked number 1 in the open dataset lingo QA. This is going a little bit behind the scene regarding how we train our model, the open source model. And we trained our model with 80,000 AV data. Maybe it doesn't sound too much, but we are not training our model from scratch. Our model was actually the backbone was taken from the Cosmos Reason model, which was obviously part of the Cosmos open model family. And Cosmos, the foundation model, was trained with the internet scale data with 20 million hours of real-world data. And then on top of that, there's basically Cosmos predict, transfer, and then the Cosmos reason model was trained on top of that. So this pyramid shows us basically how much data the actual model our model inherit from the foundation model, and hopefully it will also show great generalization capability in the field as well. However, taking the Automotive open source model to production will still take quite a bit of work. Hopefully this is not very surprising to anybody here. So to build a production-ready, basically, model, you have to make sure the model is fine-tuned to work well in all different scenarios. And this is the typical pipeline, which is what we use for internal effort as well, which I'm going to show in a later slide regarding how to fine-tune the Automotive model and get it ready for production. So you will need lots of data set, obviously, either through data collection or through synthetic data, which Cosmos can actually help over there as well, which is also open sourced to public. In the middle, obviously, you have to prepare the data set and train the model, and then basically when you release to the car, and then basically you have to get the let's say the failure mode from the road and basically feedback the data to the model training. So the tools are very important here. One is basically obviously when we prepare the data set, you need a good searching and curation capability, and also on the right side, simulation and validation is super important. In the Gen AI, kind of way of developing AV. So to help, again, the ecosystem to be able to train the model, we are not only open source the model itself, we are also open source data, which is right now at this point it's 7,000 hours of high quality data which we collected in the DRIVE AV development phase. To the best of my knowledge, this is by far still the largest data set, open source data set out there. And this is probably not enough for training, But this data has good, basically, diversity. It's collected into, in 25 countries, it will be very well suited for evaluation and testing. And we are also, as I said, tooling is very important. You need good tooling for searching and curation, and you need a good tooling for validation and simulation. And towards this end, we are also basically make NeuRec, which is neural reconstruction, as a tool to be available to public soon. Not yet, but in the next few weeks. And the NeuRec is a super powerful, basically, tool, which is absolutely needed for developing AV stack, especially the end-to-end model. So this video, hopefully I haven't clicked yet. Okay. So this video shows the, the cameras, and you can see, we can really reconstruct the pixel when the vehicle is changing a different pose. This is very critical for any, basically, closed-loop evaluation of the stack of all of the end-to-end model. So this technology is pretty mature. It's getting more and more mature as we speak as well, partly because it's massively utilized in our internal effort, Drive AV development. We are running 2 million simulation tests based on NeuRec on a daily basis to develop our stack. So there's a, famous phrase, we are eating our own dog food. And I'm very confident about the quality of this tool, and hopefully this can help the community. Well, NeuRec is not only about basically doing just replay, different trajectory and reconstruct the pixel. You can do more about that. And as part of the NeuRec open source effort, we also open sourced Fixer. These are two Gen AI models. One is Fixer. The other one is basically Harvester. The Harvester can actually harvesting any object you see from the field and save it for other use. For example, you can plant it in other videos. So this slide shows how we can leverage this capability, not only use NeuRec for replay, but also use it to insert and modify behaviors of the object. By doing this, we can increase the data diversity or variety by order of magnitude, from the data we collect from the field. So there's a few examples here. I will just quickly click through them. Essentially, you can, obviously, you can just do the reconstruction. You can also basically insert a scooter here. I'm not sure if you guys can see. I cannot see very well. The screen in front of me is extremely small. Then basically, you can also change, modify the obviously trajectory when this kind of object shows up, and then feed back, train a different model and deploy it to the car. And the other one, which is extremely important and extremely powerful, is Cosmos transfer. Again, Cosmos transfer, as I showed you guys briefly in the data pyramid, is a part of the basically a Cosmos family. And what it does is basically you can render any sequence into a different environment. And there's some example here. Oops. Can we go back to the previous slide, please? Yeah. So there's a multiple example here. Obviously, you can just add a prompt of different weather, different lighting, and even in different cities, in different essentially terrain. This is again another way to bring a lot more variety and diversity into a data set and train the model. All right. Last but not least, let me spend time talk about the Drive AV. And we have a pretty sizable team working on Drive AV right now. And obviously, NVIDIA is pretty well known to work with the industry to provide AV SoCs. As I mentioned, 10 years ago, Parker enabled the first version of Autopilot. And the next generation, basically Xavier and Orin, they really started the massive transform or bring up of AV technology in China and the rest of the world. And right now, basically, at least in the China market, you cannot really sell a car, new car, without a good AV capability in it. And we announced the Soar as well. It has been in the market for a few years, actually there's already OEMs taking Soar to SOP, and we are also seeing very good trend in the rest of the world market as well of Soar adaptation. Soar is, as I said, a part of the Hyperion basically ecosystem, Hyperion platform. For everybody who's adopting Hyperion, will use Soar as an in-car AI supercomputer. It's probably less well known that NVIDIA worked on AV stack also for a long time. DRIVE AV was kicked off 10 years ago as well. And in 2017, actually, we had our internal, which was a little bit ahead of its time, I would say, end-to-end model-based approach, basically for AV, which is called a PilotNet. And then basically, with many years of progress, and we secured a partnership with Mercedes in 2020, which was 5 years ago. And then basically, there's the JLR happened and Lucid happened, I cannot say much yet, but basically we'll have more more OEMs getting into the DRIVE AV basic ecosystem. And last year, 2025 was the first year after 5 years of partnership. We deployed our technology to all Mercedes vehicles globally, except China. We are expecting to roll out our address to address L2++ capability throughout this year in Mercedes vehicles, which is going to be super exciting. And we are also working on, as we speak, JLR and the Lucid customer fleet as well. Our DRIVE AV stack is actually a hybrid end-to-end and a classical stack. This is very important because we get the human-like drive experience from the end-to-end model. This is very well known. But the whole industry have developing AV and ADAS based on basically FUSA and ISO 26262 standards. And this kind of interpretable safety is very important to the industry. So having a hybrid stack, you can achieve both. Number one, you can still have human-like driver experience, and meanwhile, without compromising basically the safety interpretability. So this slightly busy diagram shows our stack. What's important here is our Mayo, which is the production version of Mayo, is our end-to-end model running in the stack. By the way, we're running everything here in one Orion. And basically, this is a LiDAR-less and mapless stack. And on the right side, it's our classical stack. And on top of that, basically, we have a safety arbitrator, which can guarantee safety when the stack is running. And with this stack, obviously, we are delivering parking, we're delivering active safety, and we are also delivering advanced AV features, including highway L2+ with a hand-free capability, and L2++, which is the address to address or park to park in urban scenarios. And this slide shows a little bit how we take our Mayo to production in the internal DRIVE AV effort. It's very similar to the slide I showed before, and we are iterating super fast. We have iterated, basically, we started developing this end-to-end model about a year ago, and now we have iterated 3,500 times. And roughly speaking, we are iterating 10 versions every day. Basically, we are also using, obviously, a sizable GPU cluster to be able to iterate this faster. this fast. And also, as I mentioned, simulation is very important for this end-to-end model development. And right now, basically, our technology have enabled from test in the field until a model is ready. Again, every new rack is a model. You have to build this model and use it in replay and the CL and the closed loop evaluation. Right now, we can contain the whole hours within turnaround time within 6 hours, and we believe that we can take it down to a few hours in the near future. So again, this is a massive effort, and the middle block is is similar to the AlpaSim we open sourced to public. But this one is slightly more because it have to be able to do a closed loop evaluation of a hybrid stack. So you can run a classical stack and the end-to-end model and use this to get a good evaluation result. Well, this one explains roughly how guardrail work with a classical stack running again side by side by the end-to-end model. We have a cyclist ride on the side, and because its shoulder is ending, to end up basically coming to the road. So when it's green, shows our model was running it. When it's classical, the arbitrator changed the model to classical. Essentially, it will say, okay, this current trajectory is not safe enough. The classical trajectory is better, then it will seamlessly, almost like with zero delay, it can transfer, transit, I would say, to a classical trajectory and to maintain safety. And as we speak, we just started basically, worldwide scaling as well for our L2++ stack. And this is showing we are basically driving pretty much everywhere in the world. And we expect that by the end of this year, we should be able to scale the technology to all of the US and a few cities in Europe. And the next year, we want to basically make it available globally. And another important point to hit is basically our current software structure is actually very much scalable, or extendable to L4. So this slide shows what this, the architecture will look like when we enable this kind of capability, our stack in an L4 setting. You will have a main ECU, and you also have a satellite ECU. In the main ECU, it's pretty much running the L2++ stack we are running right now. But on top of that, it will take additional sensors from the satellite ECU to make the main ECU capability even better. And on the satellite ECU, this is our safety redundant stack. It's mostly going to be classical based, but it will also have the MRM, or minimum risk maneuver, when basically a single point of failure happens. So in this way, basically, we can use the same code repository and delivering L2++ and L4 together to our partners. All right, this is our high-level, roadmap. As I said, basically, this year we are trying to scale L2++, from address to address. And starting from next year, we want to start the initial deployment of our L4 fleet. And by the in 2028, we will basically deploy L4, in passenger vehicles with our partners. And basically, I want to. This is Hyperion is catching a lot of attention, I would say, and we are having new OEMs joining basically Hyperion ecosystem almost, I would say, every month. And we have 4 new OEMs joining the Hyperion ecosystem: BYD, Geely, Nissan, and Hyundai. all of them are, for all of the top 10, basically, OEMs globally. And again, we see great benefit of, having a common sensor suite in the compute platform across different OEMs. And we are also I'm very happy to announce our partnership with Uber towards L4. And by 2028, we agreed to deploy L4 technologies in 28 cities globally. We are also basically, obviously, NVIDIA is not only a AV company. Of course, we're not only a chip company. We are a full-stack AI company. And we are using our AI capabilities to work with OEM globally on many different areas as well, including basically using Omniverse digital twin for design and manufacturing and enterprise. This is the ecosystem we are working with. Autonomy is a daunting task. It's a grand mission, but it really needs everybody to work together. And we are very happy to work with everybody in the automotive basically industry, including OEMs, tier ones, or AV software developers, to work together to get from 0.006% to upper 90s. This is the mission. All right, I think I'm running a little bit out of time, but this is the key takeaways of what I talked about today. Again, Drive AV is NVIDIA Drive is getting into a new phase, 3 computers, 5 layers of service, and we are trying to basically, on the Hyperion side, we're trying to get as many as possible OEMs to share the same sensor in the computer platform. And we are also trying to work with Uber to create a large data set for the ecosystem developer AV. And we are bringing halos, we're enhancing halos significantly from just the operating system to a basically a safety guardrail so that everybody can deploy end-to-end AV stack on Hyperion, our hardware platform. And we announced our Mario 1.5, which is the next generation of our Mario. And also basically on the application side, NVIDIA is working super hard to take Drive AV to the next step, which is really basically this year it's about scaling of L2++ and also get the technology extend to L4. And on the infrastructure side, because simulation and the validation with Gen AI technology is super important, we are also open sourcing our foundation models and also NeuRack and the Cosmos transfer models so the industry can use to enhance their data set and accelerate their AV development. So this is what I want to talk about today. Thank you for your time, and hopefully you can enjoy the rest of the afternoon. Thank you.